Hello everyone. Last video we looked at how to add and subtract vectors graphically. So today I want to look at the way we can use geometry to actually add our vectors, and we don't need to worry about using a ruler and protractor. So here in front of us we have two vectors A and B. I have used the protractor to measure the angles. Vector A is at 60 degrees to the horizontal. Vector B is at 30 degrees to the horizontal. Now I want to define what these vectors are. So let's say that these vectors A and B are velocity vectors. Now, I'm not going to worry about the scale because we're not going to actually calculate the result graphically. But let me define the values. So let's say that vector A represents, let's say this is 40 meters per second. Of course, that is 60 degrees northeast. And let's say that vector B is equal to, it's not quite half. Let's say it is 25 meters per second at 30 degrees northeast. And I want to find the resulting vector of adding these two vectors together. All right, to recap what we did last time, if I wanted to add them graphically, we did things like this. I would have to arrange these vectors and carefully arrange them tip to tail. Now, it didn't matter which way we actually arranged them. That is, I could do vector A first or vector B first, but what was important that I did not affect their size or direction. And so what I would do is keep my angles constant. And I would draw the resulting vector from where the first vector started to where the last vector ended. So the resultant would be something like this. And I would need a ruler and protractor, to solve the problem. Now, instead of adding the vectors graphically, instead of working with the whole vectors, last time we learned that I can always add vectors together. That means that just like any number, instead of working with the vector A, I can work with two vectors that add up to A. We call these two vectors that would add up to A the components. Now, I could choose any two vectors that would add to A, but we'd like to choose our vectors, our components, in the X and Y direction. Okay, so we have our two vectors A and B, and I would like to, instead of adding these vectors graphically, first break them up into components that I can use trigonometry to work with the arrows. So let's start with vector A first. Instead of working with the vector A, I can draw two vectors that add up to A. So I'm going to draw a vector here, and I'm going to call this AX, vector AX. That is the X part of vector A. And then if I draw another vector here, this would be vector AY. And this is represents the Y part of vector A. Now notice that we've just made a right triangle. Also notice that vector AX and AY are arranged tip to tail, and so they would, in fact, A would be the result of adding AX and AY together. I can do the same thing for vector B. I can pretend that vector B is made up of some vector BX, then some vector by that together add up to vector B. So what I would be saying is that here, vector A is equal to the sum of the vectors ax plus ay rather, and vector b is the sum of vector bx plus by. Well, I can use trig to find out what these components are. That the sine of the angle is equal to the opposite side of the triangle divided by the hypotenuse. The cosine of an angle is equal to the adjacent side divided by the hypotenuse. And the tangent of an angle is equal to the opposite side of the triangle divided by the adjacent side. All right, so AX touches 60 degrees, so that is in the adjacent side. So I can say that cosine of 60 is equal to AX, the magnitude of AX divided by the vector A. The actual vector is always the hypotenuse. Well, cosine, that means that AX is going to be A times cosine 60. Well, cosine 60 is a half. That means that vector AX is going to be equal to half of 40, or it's going to be equal to 20 meters per second. Similarly, AY is going to involve the opposite side of the triangle of the hypotenuse. That's the sine. So I can say that AY is equal to A times the sine of 60. That's going to be equal to 40 times the sine of 60. Well, the sine of 60 is about 0.866 if you check on your calculator. That means that AY is about 35 meters per second in the vertical. Now, I've rounded a little bit for this one. But more importantly, we're working with degrees here. So you need to make sure that your calculator is in degrees. So if you don't get these values, double check that you're not in radian mode. All right, I'm going to do the same with B. I know the x side of B is going to involve the cosine function. So this is going to be equal to 25 meters per second times cosine of 30. Well, cosine of 30 is the same value as the sine of 60. So this works out that bx is equal to, let's see, we have 0.7 times 25. That is about, I'm rounding to 22. It's 21.75, but I'm going to round to 22 meters per second for this discussion. And by is going to be equal to 25 meters per second sine of 30 degrees. Well, the sine of 30 degrees is the same as the cosine of 60 degrees. So that means that by is going to be equal to 12.5, or approximately 13 meters per second. All right, I'm rounding for the purposes of to make the calculations a bit easier in the notes. If you're working on the website, you should work to 3 sig figs. These are rounded to 2. All right, well, why did I go through this trouble? Well, if I wanted to add vectors A to B, there should be no difference between adding vectors A and B and adding the parts of vector A to the parts of vectors B. So I'm going to clear some space, and let's first remind us that what A and B would be graphically. Remember, if I wanted to add A plus B, I would arrange the vectors like so. And remember, the resultant was drawn tip to tail from the start of vector A to the end of vector B. But instead of adding the vectors, I would like to add just the components. So here I'm going to first add the x vectors together. So notice here I have now added vectors ax plus bx. And now let's add these y vectors in. So take a look. Ax, instead of adding just the two vectors a plus b, I see that adding the components, the x and the y's together, and these are also all arranged tip to tail, start and end at the same place as these two vectors. So that is, if I drew in my resultant now, that's the same resultant as I got before. So it doesn't matter whether I add my two vectors graphically or whether I first calculate the x parts of each vector and the y parts of each vector and just add the x and y parts. Well, the advantage of that is I don't need to worry about scale anymore because I'm just using trig to find out how large these are. So what we do is we say that the x parts added together, these make up the x part of my result. Well, Rx, that means I know what Ax and Bx are. Bx was 22 and Ax was 20. That means the x part of my answer, Rx, is going to be equal to 42 meters per second. Similarly, I define the y components added together to be equal to the y part of my answer. So that would be about 13 plus 35, so that makes it about 48. Well, that's not my answer. My actual answer is vector r, but at this point you can probably see how we're going to find out what r is. So the size of r will be equal to the the magnitude of r will be equal to the square root of the x portion of r and squared plus the y portion of r squared. In this case, the magnitude of r would be equal to, well, that's 42 squared plus 48 squared, square root the answer, and I get about 63.8 or about 64 meters per second. But again, it's not complete unless I find the angle as well. So to get the angle, I'll do the inverse tangent. Of the y side, or the opposite side over the adjacent side, which is ry over rx. And if I do that, that's the inverse tangent of 48 over 42. It'll be very close to 45. In fact, it's about 49 degrees. 48.8 and actually to 3 sig figs, but I've done everything else to 2, so we'll leave it as that. All right, so this result is incredibly important, because this allows me to combine any number of vectors using trigonometry to find the x and y pieces of those vectors. And then I can tell you the answer of adding those vectors without worrying about drawing them to scale. So we are adding vectors by components. Consider any two vectors. Vectors A, making some angle with the axis, and vector B. And these vectors can be any type. So first, we draw and calculate the x and y components of these vectors. So the components are simply the vectors drawn in the x and y direction that would add up to the original vectors. And remember, the x and y components will always make a right angle that is 90 degrees with each other. And they will always add up to the original vectors. The next step is to combine the components to find out the components of the result. So the x part of my answer will simply be the sum of the x parts of the vectors I am adding. And this works with any number of vectors. If I had 3 vectors, I would have 3 x components, 4 vectors, etc. And the y part is simply the sum of the y components. And remember, we used trig. We knew that cosine of the angle to the horizontal was equal to ax divided by the actual vector a, and sine of the angle was equal to ay over a. And then finally, 3, draw and calculate your resultant. Sorry about that. So, if I want to know the result of adding vectors a and b, well, that's simply going to be whatever our x is added to whatever our y is, because this is going to be the same as the x part of my answer plus the y part of my answer. And I can draw the result by going from the start of the x vector to the end of the y vector. The size of r is going to be equal to the square root of the x part squared plus the y part squared. And the angle it makes with the horizontal I can get with an inverse tangent. And that is how we actually work with vectors.